if you have any interest in baking technology or cereals, be a good class to take. It does fulfill, if you're an undergrad, it will fulfill your part of your processing requirement. It'll move you closer to graduation. So let me know if you're interested. Like I said, I am hoping to have a couple more people register for it. So if you have any interest, please do that. We talked about the exam, second exam, a little bit on Monday. So I don't know that I need to say a lot more, but it's starting Saturday, starts on Saturday, and you'll have until Monday evening to complete it, or Tuesday evening, sorry. And format's the same as before, so it shouldn't be too much of a surprise. It'll cover additives and carbohydrates. Any questions on it? The way I set it up last time, the answer was yes. This time I've not set it up that way. So you can leave the exam and come back and continue it. So if you don't want to complete the whole thing at one time, that's fine. Or if you lose internet connection, you can come back and get back on. But once you hit submit exam, so once you hit that button, then you won't be able to do anything else on it. So I don't know. I wish that submit exam wasn't right next to the next question button. I think that's a poor design there, but anyway, make sure not to hit the submit until you're all done. It is the same. So the questions are randomized, and you can't go back. Once you answer a question, you won't be able to go back to that question again. So you can only move forward, but you do have as much time as you need again. And if you don't complete it all at once, that's okay. And I did notice that a lot of people took a lot of time to complete that exam. Several thousand minutes, for example. So people are really using that unlimited time to the fullest extent possible. All right, let's see if we can get through this. I don't know if we can, but we'll try. So we ended here on, actually, let me bring up the chat. I sometimes forget to do that, and I miss questions from people online. So we ended on carrageenan, so we'll start on pectin here. This is the structure of pectin. Looks pretty nightmarish, I think. Very complex structure. But in fact, the pectin that we use in the food industry is very simple. And so the reason for that is when pectin is being extracted from orange peels or apple cores, typically that's where it's from. When it's being extracted, they extract it in a dilute acid solution, typically citric acid solution. And in the process of doing that, these complex branches here are hydrolyzed off. So we end up, and the orange peels and the apple cores that we typically extract pectin from are mostly this straight chain version. So they have very little rhamnose in them. Rhamnose are these white sugars here in the backbone, and they create a kink. And so they're not as desirable for gelation. And so we try to select sources of pectin that have a homogalacturanan backbone with as little rhamnose as possible. And then in the process of extracting it, these complex branches here, complex side chains, most of them would be removed. And so when we talk about pectin and its use in the food industry as a thickening agent, as a food additive, we're mostly talking about polygalacturanan. So a lot of galacturonic acid units linked together in a row. And that's all. So this is the structure here. The things that you want to notice here is carbon 6. So you see you have some that have this methyl ester here, and then some that have the free acid. And that's really important for the functional properties, the ratio between those two. Because in one case, you have a charge, a negative charge, that is going to be characteristic of what we talked about with anionic polysaccharides. And then here you have no charge, and in fact, a little bit of hydrophobic characteristic. So there's going to be no repulsion here. There's actually going to be some attraction because those methyl groups are going to want to come together because they are hydrophobic in a very hydrophilic environment. So, so we have two different types of pectin. We have one called high methoxypectin, and usually we abbreviate it HMP. So high methoxypectin, which actually should be called high methyl esterified pectin, but they long time ago started calling it methoxy, and the name stuck. So it's high methoxypectin. And so that would mean that typically it has about more than 50% methyl esterification. And then we have low methoxypectin, and that just has, less than 50% methyl esterification. And the naturally occurring version is the high methoxypectin. So normally, if we don't do anything to it, we just extract it, we're going to have high methoxypectin. And this is what we use for thickening jams and jellies and in other thickening applications to form gels when there is high concentration of sugar. And the low methoxypectin, you have to make that. So that would be made by demethylating or cleaving that ester linkage, cleaving off this methyl group. So you can do that with alkali, with acid, or with an enzyme. Typically, it's done with either acid or alkali. The enzyme tends to cleave non-randomly, so the enzyme will bind and cleave like a section, and that's not as desirable. It's better if you have kind of a random demethyl esterification rather than in chunks. But it can be done either way. So high methoxypectin, that's going to be useful for a jam or a jelly thickening, so it can form a gel. High concentrations of sugar at low pH. So when we talk about high concentration of sugar, it's probably something like greater than 65% sugar. So a lot. So that's, typically we're talking about jams and jellies that are used for this. So 65% sugar is close to saturation, so very high concentrations. And then low pH, we're talking about something like 2 to 3, so quite low. We need all that sugar to dehydrate the pectin. Remember, sugar is going to grab onto a lot of water, and that's going to dehydrate the pectin and allow it to form junction zones, because otherwise it's just very soluble. So low methoxypectin forms gels also in the presence of a divalent cation. So if we want to gel low methoxypectin, we will add typically calcium chloride, and that calcium ion will allow these negative charges to associate through a salt bridge and form a junction zone that way. So you can use this in low sugar applications. Also, you need a little higher pH. So let's say 4 to 5. Well, let's say 3 to 5. So because if you get too low, then you protonate all of these groups. And so you don't get the advantage of forming that salt bridge anymore, because it's not going to form a salt bridge if you protonate all those negative charges. So we'll just go through a couple of examples to reiterate some of these points. So here we have two pectin chains, and they have their demethylated uronic acid sticking out here. So you see the negative charge and then the methyl version. And if you, just like you imagine, if you had something like this, where you have two negative charges next to each other, that chain would repel itself. The two chains would repel each other. And where you have methyl esterification, those chains would want to associate with each other. So you can see how that ratio between the methyl esterification and demethylated is really important for those functional properties. So here's a function of pH. So if we lower the pH and we protonate some of these negative charges, then those will no longer repel each other and they will come together as well. So anywhere where we still have a negative charge, those are going to still repel each other, but that repulsion will be neutralized when we protonate those carboxylic acid groups. And then here's forming a salt bridge. So in the case of low methoxypectin here, where we have a lot of demethylated groups on this chain, so if we add this divalent cation, then we can form this salt bridge. If we have a monovalent cation like sodium or potassium, then we can neutralize those negative charges so they don't repel each other so much, but they won't associate in the same way that they do with a divalent cation. Okay, some of this stuff I mentioned already. So we need a low pH. So before I said 2 to 3, it's just low, something like either 2 to 3, 2.5 to 3.8. We need a lot of sugar, and we need a lot of methylation so that those chains can come together. In commercial high methoxypectin, the gel forming capacity is evaluated on this SAG scale. What is it? I wrote down what SAG stands for because it's kind of an interesting standard acid in glass. It's not important, but it's interesting because like in the 50s when they were developing this, it's basically you put the gel into a beaker or a container, and then once it's gelled, you dump it out and then measure its height after a period of time. And because they would use this special glass beaker, it was called standard acid in glass method. But anyway, the sag scale is still there, and so basically you just add a portion of pectin to this solution that has 65% sugar, pH 3.2, and just evaluate the gel strength. So we'll get a score. There's also things, I think here, these are probably more important. There's two types, a rapid set and a slow set. And you see that the DE there stands for degree of esterification. So if you have a really high degree of esterification, then you're going to have a rapidly setting pectin. And then if you have a lower degree of esterification, still in the high methoxypectin range, but lower, then it's going to be slow set. And a rapid set is going to be really useful for jam. So jam would be a fruit spread that has chunks in it, chunks of fruit. And you know, fruit typically is going to float on water. It's going to have some air inside of it, and so it's going to float. So when you cook that jelly or that jam, those chunks of fruit are going to want to float to the top. And so what you want is something that's going to set really fast so that those chunks will stay evenly distributed in that jam and won't float to the top. And then you have a slow set that you want to use for jelly, something that is made from juice that has no chunks in it. Because when you're cooking that jelly, as you're stirring it or as the kettle is being stirred, there are air bubbles that get forced into there. And you want those air bubbles to float to the top before the gel sets so that you don't have a bunch of air bubbles in your jelly. So rapid would be for jam, slow would be for jelly. So I mentioned already, low methoxypectin is less dependent on pH and sugar concentration, more dependent on this divalent cation or the ionic strength that's present. And it's used to thicken low and no sugar jams and jellies. And it's also increasingly being used to thicken milk products. Of course, high ionic strength, right, in milk products. And there's a little bit of a negative attitude out there in the consumer realm for carrageenan because of its sulfur groups, sulfate groups. And so where carrageenan was almost ubiquitous in dairy products, it's starting to be used less, and they're replacing it with this low methoxypectin. Next, we have cellulose. So cellulose is, of course, naturally occurring. It's a very abundant dietary fiber in our diet. But when we modify cellulose through chemical means, then it becomes a food additive. Here I just show the structure. This is the naturally occurring structure of cellulose. When we, oh, I forgot, I hid this one slide. Let me show it to you. So here, this slide shows how we get purified cellulose for the use in food industry if you want to add it as a food additive, typically starting with wood chips or sawdust, and then going through this process of really, really, really high alkaline treatments to purify that back all the way to cellulose. in the process of that purification, the structure of this cellulose here changes a little bit. So the structure is a little bit different, the crystal structure, but ultimately it's this beta-linked glucose molecule. Okay, so we have, first of all, microcrystalline cellulose. Microcrystalline cellulose is simply acid-treated cellulose. So cellulose is going to have crystalline regions and amorphous regions. And the acid is going to be able to hydrolyze the amorphous regions, the regions that are a little bit more bent or not as tightly packed. And so we end up with all these little tiny chains of cellulose that are several chains linked together in a crystal. So that's where it gets its name, microcrystalline cellulose. It doesn't have tons of applications. It has one that we'll talk about, and then another one that I'll mention now. It's used as an anti-caking agent. So it's going to help things to stay free-flowing, like salt or cheese or you know, a powdered spice mix or something like that. Okay, so now we can talk about chemically modified cellulose. So we can take cellulose at a very high concentration of alkali and treat it with a reactive compound, several different kinds, and form chemically modified cellulose. All of the chemically modified celluloses are ether derivatives. So they're all etherified. You know, most of the starch modifications were ester modifications. Here, they're all ether. There's no other types of linkages to the cellulose. Same kind of deal here. Since we're still a glucose polymer, we can have this degree of substitution of 3. So we can substitute at any one of these 3 hydroxyl groups that are indicated there with stars. We can change all of these variables here to get different properties of this modified cellulose. So just like we talked about with xanthan, one chemically modified cellulose is not necessarily going to be just like another. So first we'll talk about carboxymethyl cellulose. So we mix cellulose with sodium chloroacetate. This is sodium chloroacetate. And the chlorine atom here on the methyl group is what reacts. So it's not going to be the carboxylic acid. This is not reactive enough. So it's going to react on this side and form this structure. So we form an anionic derivatives there. And here's this other functional property of microcrystalline cellulose. So if we mix microcrystalline cellulose and carboxymethyl cellulose together, then these microcrystals here can help the carboxymethyl cellulose to form junction zones and form what is typically referred to as a pseudogel, like a fake gel. And that's because the microcrystalline cellulose here is a particle. It's not something that's really dissolved in the water. But this particle allows those polymers to stick together and form a pseudogel. The degrees of substitution for all of these celluloses are much, much higher than we saw for starch. So for starch, we typically saw modifications around, at the high end, they were 0.1, but typically they were 0.001 or something like that. The modification for carboxymethylcellulose is close to 1, which means that just about every single glucose unit is going to have this carboxymethyl group on it. And that's necessary because, you know, cellulose is so water insoluble. And you've got to substitute it a lot for it to become soluble in water. So the degrees of substitution here are going to approach 1 for this one. So quite extensively derivatized. Methylcellulose is another derivative here where we just form this this is an actual methoxy group here. So we introduce a bulky group and a little bit of nonpolar characteristic. So the degrees of substitution for this one are actually going to be above 1, about 1.2 to 1.5. So that means that every glucose unit is going to have this methyl ether on it, and some of them are going to have 2. And because of this methyl group, this polymer is on the borderline of solubility. So we introduce a lot of these bulky groups onto it, so it does actually dissolve, but they're nonpolar bulky groups, and so it's barely soluble. And because of its barely soluble nature, it's going to have a very unique functional property. And that's shown in this figure here. So typically, if we have a gel and we heat it up, what happens to that gel? I didn't hear you, but probably you're right. It melts, or it gets more liquid, right? So we heat up a gel and it will melt, and then we cool it down and it will reform a gel. That's a reversible gel, but that's typically what happens. And most of the time we will actually form gels by heating that solution and then cooling it, and then it will form a gel. You think about starch, you think about all these other polysaccharides that we've talked about. We heat it up, it's liquid, cool it down, it's gel. It's the opposite with methylcellulose. So you see that here, right? So if we heat this product, here's the viscosity. If we heat it, the viscosity does go down to a point, and then once we get above 45, 50 degrees, all of a sudden we have this rapid increase in viscosity, and that's because we get gel formation at this high temperature. And the reason for that is because of its borderline solubility. That's based on hydrophobic characteristics. So when hydrophobicity is dependent on temperature. So things that are hydrophobic become more hydrophobic when we heat them up. So the higher the temperature, the more water and oil are going to repel each other. You can think about it that way. And here, the more we heat it up to this point, this polymer is now very, very insoluble. And so now it can form junction zones and form a gel at a high temperature. And so that is going to introduce, that's its unique functional property. And so it's added to a lot of products where you want it to be liquid or free-flowing at room temperature, but you want it at a high temperature to be gelled. Just, can anybody think of anywhere where we would want that to be the case? This is a tough question, but as soon as I tell you the answer, it'll make sense. So, what about a chicken pot pie or a berry pie, a fruit pie, something like that? So it could even be like a chili or something like that. But these types of products, when you heat them up, it would be nice if it were very thick, because then you would get less stuff leaking out of the crust. Or in the oven, you would have less bubbles flowing out over into the oven. So when you heat it up, if you put this in, it will form a gel so that you'll get less boil over or less leakage from your crust. And then when you cool it down, it's going to be like a gravy if you're talking about a chicken pot pie, or it's going to be, you know, just a nice kind of soft gel if you're talking about a fruit pie or something like that. So that is a really unique functional property of this and very useful for this particular polysaccharide. It does have another use. It is really common to use in frozen desserts like ice cream as well, for controlling ice crystal formation. And you know, because it's borderline solubility at high temperature, the lower the temperature you go, this is opposite. Everything's opposite with this one, remember. So the lower the temperature, the more soluble it is. So it's going to have even more solubility in frozen applications. So then that's where its second use is. Hydroxypropyl cellulose here. We saw this compound before. Propylene oxide is reacted with cellulose, and we form this hydroxypropyl cellulose derivative. I haven't introduced to you a term called molar substitution, but in the case of having propylene oxide as the reactant, propylene oxide, when it reacts, it forms a new hydroxyl group. You see that right here. So you can actually have another propylene oxide react with this hydroxyl group and form like a chain of hydroxypropyl groups. And so in the case of this reactant, you can actually have higher degrees of substitution than 3. And usually we call them molar substitution instead. And in fact, this compound typically has a molar substitution of 4. So that means every single hydroxyl group has been substituted on the cellulose molecule. And then we do have some that have actual chains of propylene oxide groups on them. So very, very extensively substituted. Hydroxypropyl cellulose forms films. So it's very useful in aerated products. It will form films around an air bubble, for instance, and stabilize that air bubble. So you can see that in this you know, gelled product here, or aerated product here. So I think it's modified cellulose here. It's likely hydroxypropyl cellulose. But the characteristic of this is that it forms these films, and typically it would form this film around an air bubble so you can get it to be very stable. Okay, next we have gum acacia. And so gum acacia is a polysaccharide gum that also has protein. So these big circles here in this picture, these are the carbohydrate portion. So instead of drawing these as a line, they've drawn them as these blobs because it's super branched, very branched, like more extensively branched than amylopectin. Very branched polysaccharide here that has some protein that is covalently attached to that carbohydrate. And the protein is actually quite hydrophobic, this protein. And so the characteristic of gum acacia is that it's an emulsifier. Because we have this highly branched carbohydrate block that is very hydrophilic, and then we have this protein that actually has quite a few nonpolar amino acids and can help to form an emulsion. So gum acacia is an emulsifier. It is a non-viscous. So all these other polysaccharide gums, we've been adding them for viscosity or gelation. Gum acacia is not added for viscosity. In fact, you can have 50% solutions of gum acacia, and they'll be viscous, but not anything like a 1% solution of xanthan gum. So we can say that they're non-viscous. They're used a lot in candies and beverages. So like candies, not necessarily like real exciting candies. Things like cough drops, lozenges, things like that is a common use for these. And then beverages, it imparts some body to beverages, and it will also help to emulsify flavor and color compounds in that beverage. So there's gum acacia. Let's switch gears and talk about emulsifiers here. We've talked about them briefly already. So I'm just going to go into a little more depth with the few minutes I have left here. So what I want, what you want to remember, of course, is that emulsifiers are emulsifiers. Right? So they do what's shown on that beaker there. They will emulsify fat into an aqueous phase, form these micelles, and that's what we typically think. But I do want you to recognize that emulsifiers have many, many other functional properties besides just that are super important. So some of this is I've mentioned before, but we have mono and diglycerides. So this picture here is an alpha monoglyceride. Alpha because the fatty acid is linked to the glycerol at the 1 position. A beta monosaccharide, or a beta monoglyceride, it would be linked at the beta position, at the 2nd hydroxyl group on the glycerol. But alpha are the desirable ones. So alpha monoglycerides would be the ones that we would typically use in bakery applications, which is the #1 application for these monoglycerides. Lecithin is another very common emulsifier that is naturally occurring. It's the only naturally occurring one that we isolate and add to foods. We have lots of synthetic ones, but this one is a naturally occurring one. It's a mixture of phospholipids. Here it's a mixture of phospholipids. The predominant phospholipid is phosphatidylcholine, which is shown here, but there are other phospholipids present in these lecithins. We also have monoglyceride derivatives. So we can take a fatty acid and mix it with an acid or an alcohol and form a ester there and form a unique or a new emulsifier. So one example is here. So these are polysorbates. So we start with sorbitan, which is made from sugar, and ethylene oxide, and we form this polyethylene derivative of sorbitan. And then we can react it with a fatty acid here and form a polysorbate. And you see this ester linkage that's formed between the side chains, the ethylene side chains, and the fatty acid. The number here, 60, you can have 60 or 65 or 80 or 85. Those just determine what type of fatty acid there is here. But these are also good film formers. So they're present here in this Cool Whip here, this whipped product, as a film former and a bubble stabilizer. Here's another alpha monoglyceride. The one I'm highlighting here is propylene glycol monostearate, this PGMS. This is the most commonly used one. Very common in cake mixes here. You see this propylene glycol mono and diesters of fatty acids. That's the PGMS. It's there to incorporate air into the batter, so we can have a more leavened cake. This sodium stearoyl lactylate is also a alpha emulsifier made by reacting lactic acid with stearic acid. Emulsified shortenings, very common. These emulsified shortenings typically will contain mono and diglycerides. This is why mono and diglycerides are the #1 emulsifier. And in these shortenings, what their role is to keep the shortening in its beta prime crystal structure. So the fat that's used to make any of these shortenings is polymorphic, which just means that it can form many different types of crystals. And the ones that we want in bakery shortenings is beta prime. That one is going to allow us to incorporate more air into a batter. And it's not necessarily, sometimes it is, but not necessarily the most stable crystal. So over time, we can get reversion to some other crystal form. And the monoglycerides will help to keep that shortening in its beta prime crystal structure. Breads, we also have tons of emulsifiers that are added. We have datum, which is an acronym for diacetyl tartrate esters of monoglycerides. I don't know if I should write that. Diacetyl tartrate. Obviously, an emulsifier, monoglycerides reacted with tartaric acid and acetic acid. Helps to strengthen gluten, make it more elastic in the dough, in the bread dough. And then we have also monoglycerides here added to prevent starch crystallization and prevent staling. Emulsifiers are also wetting agents. So they will decrease the surface tension of water. And so if you have this green solid surface here, and we put water on it, it's going to bead on the surface of that solid. And when we add an emulsifier, that surface tension decreases, and so it's going to spread over that solid surface. So this is really important in condiments, where we have some particulates in there, some solids, that we want them to be soft and creamy and not sandy. So we can put in an emulsifier so that that solid will be coated and softer. We talked about heat transfer during frying already. One thing that I wanted to mention here is that if you look at the ingredient statement, for most frying shortenings, you will not see emulsifiers added. And that is because at those high temperatures, the triglycerides in the fat, and also because you have so much water here, the triglycerides in the fat will hydrolyze to fatty acids and glycerol. So you get some, I guess, production of emulsifiers in the form of just fatty acids during the frying process. And in an industrial frying application, the frying oil is typically like continuously replaced. So you don't go in with a new batch of oil and start frying and then empty the tank and then fill it again with new oil. Typically, you just have a continuous process where there's new oil always being added to the old oil that already has those naturally occurring free fatty acids that act as the emulsifiers. We have beverages where we want them to not be clear. We want them to be cloudy. And so in order to make them cloudy, we will typically add traditionally we would add this heavy vegetable oil. So this brominated vegetable oil. Bromine, very heavy atom. So if we add it to these fatty acids in a vegetable oil, it will increase the density of that oil from about 0.9 to what I show here, 1.2 or 1.3. And so that is going to enable us we can dissolve flavor compounds in that oil and then mix it into the water and it won't float to the top. So that's typical. The synthetic ester gums do the same thing. They're newer and probably less detrimental to health than brominated vegetable oil. So if we don't add this, if we leave this out, then the flavor compounds and color compounds don't mix into the water very well, and they float to the top. And we get a defect called a ring defect. So you would have like a ring of flavor up here at the top, where it would be like really orange, and then the rest would be clear. And so we have to add these kinds of things to get those flavor oils to go evenly distributed throughout. And on the flip side, we want some things to be clear, like apple juice, beer, wine, things like that. So these have to be clarified, oftentimes by aluminum silicate, by these solid compounds that have a lot of negative charges that will attract these compounds that cause the clouding. And then this slide, I have some specific ways that we can clarify apple juice, for instance, or beer. We talked about one anti-caking agent already, microcrystalline cellulose here, but I have a couple others listed here. Really just compounds that will absorb moisture and keep things free-flowing. Lots of different anti-foaming agents. I listed a few here. There's many, many others. And then there's even more for specific applications, like in extraction of sucrose from sugar beets or in yeast processing. And these are just to keep all the bubbles down so that when these products are being filled into a jar or something, they don't foam over, or in this frying shortening so that it doesn't foam during frying. Okay, last slide, gases and propellants. We have some inert gases that are just used as propellants. So the nitrous oxide, just nitrogen gas, these kinds of things used to propel things out of containers like this whip topping or this nonstick spray. And then we have these reactive gases. And we're way out of time, so I'll just mention what they do when we do our review on Friday. So, and then we're done. So, sorry I had to rush through those last few. Okay, see you all on Friday. Remember to sign up for baking technology. Don't think twice, just do it. It'll be fun.
Thank you.
There is an ad code, so if you do want to add it, you do have to email me to get a code.